Hello, everybody. My name is Sophia, and I will be presenting my CAG 330 honors option project about a Bingham model for lava flow. We talked about Bingham fluids at the beginning of the semester, but I wanted to give everybody a quick refresher. So Bingham fluids require a minimum shear stress to act upon them before flow will occur. This is called the yield stress or tau naught. For example, your toothpaste will flow out of your tube when the shear stress is high enough as you squeeze it, but once it's on your toothbrush, it will not flow anymore because it acts as a solid because the shear stress is zero. In many geological models, lava acts as a Bingham fluid. Specifically, Pahoehoe flow, which is Hawaiian, is characterized by the following characteristics and assumptions, such as low velocity and laminar flow. I developed this problem that uses the Bingham model for lava flow. We have Cartesian coordinates here, while the axes are on a little bit of a tilt to account for the angle, which makes our calculations easier. We have this shear stress vector, tau yx, defined by this piecewise function that depends on whether or not the shear stress exceeds the yield stress. We can assume one-dimensional laminar flow, Newtonian behavior after the yield stress is reached, incompressibility, atmospheric pressure, and steady-state flow. The viscosity of the lava is temperature dependent as given by this equation, but we can assume that the temperature is constant throughout the lava at any given point in time. We're going to go through a couple of conceptual derivations. I won't go through every step of the calculations, but I will give a brief overview. Firstly, showing that continuity is satisfied. Basically, all these terms cancel out to zero, and we find that 0 equals 0, meaning that continuity is satisfied. Next, we're going to simplify the x component of the Cauchy momentum equation, which is this one at the top. Many of the terms cancel out to 0, so we're left with this equation. Applying some more definitions, we eventually get the second order differential equation for v of x of y. Boundary conditions are the same that we've been using, so the shear stress at the surface is 0, and we have no slip at this surface, which means that velocity is 0. Using those boundary conditions in the differential equation from earlier, we find this function for v of x, which is a function of y and temperature because viscosity is a function of temperature. Given some data here, we can see that as time goes on, the temperature of the lava will decrease, the yield stress will increase, and the height of the lava will decrease as it spreads out more over the surface of the volcano. When the lava is at its hottest, we can go through some numerical substitutions, and we can also rearrange the piecewise function for v of x to only account for y and not include shear stress anymore. We do this by finding a critical height, h naught, at which the shear stress acting on the lava equals the yield stress given to us. Then, applying the rest of the numerical substitutions, we can get this function, and when graphed, it looks like this. So until that critical height, h naught, this is a parabolic velocity profile, but once h naught is reached, we have this region called a plug flow, where the velocity is constant. That's because the shear stress is 0, because the shear stress acting is less than the yield stress. Once the lava's cooled down a little bit more, we can do the same methods as before and do some more numerical substitutions where we'll get this velocity profile. There are two main things to note here. Firstly, the magnitude of the velocity is much smaller. And secondly, there is a higher proportion of plug flow here, which is, again, this region where velocity is constant. Finally, once the lava is cooled down even more in the evening, we find that at no point in the lava does the shear stress exceed the yield stress given. Therefore, the lava will actually not flow. And that is demonstrated by this graph here. Here are my references for the problem statement and the background information. If you're interested in learning more about this topic, I encourage you to look through these sources. If you're interested in seeing more of the calculations, I encourage you to go back through the slides because they are all laid out there. Thank you for watching.